Basically, this is the quantum computing error mitigation group from Dr. McMahon's lab. I'm Akash Singh, and Arhan Reddy's here today too.
My name is Arhan Reddy, and I'm in ninth grade.
Yeah. Okay. So here's just an abstract. If you read the email, this was in there. It's just an overview, like a really quick overview. I would talk about is how quantum computing is just really efficient and it's really quick and has a lot of potential, but like the physical errors caused by vibrations, just it has a lot of error in the code and it's really sensitive too. So those are just some problems we're trying to fix today.
What is quantum computing? We can go to the next slide.
Oh yeah.
Quantum computing is a section of computing that combines quantum mechanics with classical computing, employing phenomena such as superposition and entanglement. If classical computing is like flipping a coin, quantum computing is allowing that coin to exist between the states of head and tail, revealing almost infinite possibilities. In quantum computing, we deal with quantum bits, also called qubits. Unlike classical computing, which is consisted of only zeros and ones, quantum computing uses bits in superposition between the states of 0 and 1. Zeros and ones are represented by two-dimensional standard unit vectors in vector in the form of a time the 0 qubit plus b times the 1 qubit, as shown in the bottom part. What is quantum error? Quantum computers are often affected by quantum error, which is often caused by environmental disturbances such as thermal vibrations. To protect our qubits from being affected by these errors, we utilize a structure called surface code. The surface code makes it harder for the qubits to spread out, which allows quantum computers to save qubit information across multiple qubits, thus making errors easy to correct. In quantum computing, there are two types of errors. Bit flip errors, where the zeros and one components are switched, represented by the matrix X. Phase flip error, where the zero component is multiplied by -1, represented by the matrix Z. All the other types of errors can be seen as a combination of these two. Because these errors change the information stored in the bits, they can cause data corruption and can result in incorrect information. Present error correction technology only lets through roughly 0.1% of errors, or 1 in 1,000. But quantum physicists believe that the error rate of just about 1 in a million is needed for any practical large-scale computing.
Yeah, so like the reason why the error is so prominent in these surface codes is because they actually spread when they interact with each other. Because because of this, stabilizer operations are usually used to find the path of error propagation. And a famous example is MWPM. Um, and basically what we're going to do is compare our results to this in this method in the future. Now, the problem with these stabilizer operators though is that they can only find the start and end of the error propagation. This means that we have to find the path of propagation along with the start and end shown by these stabilizer operators. Okay, and so here's our solution. We just want to find a way to find surface code error and fix it. It's just to make quantum computing better. Let's see. Okay, what have we done so far? We have generated surface code. We have implemented the bosonic bath model to introduce error into this surface code. We made a CNN and GNN. They both have their respective parts and roles in this method, and together they can find and fix these errors in the surface code. Now, here are some results. Unfortunately, the best recorded accuracy is 56.2%. We started testing about 2 weeks ago, so um, it's kind of promising, but we have some work to do. And on the right-hand side of the slide, you can see what the noisy surface code looked like and what the predicted surface code looks like. Now the black squares represent ones and white represent 0. And you see in the predicted surface code, it's gray. That just means that it's really in the middle, like the model just doesn't know which one to predict. And yeah, so okay, here's our future plans on how to fix the accuracy. So we plan to implement more hyperparameters, like changing the amount of epochs, and more importantly, changing the layout of the models, because there's just a lot of testing that needs to be done with that. However, if these don't pan out, we're going to look into other research methods that are happening currently and find out what methods they're using. We can then implement those methods into our project if we feel that our project will not be able to produce the wanted outcome.
In the late summer semester, our group collected data by creating information on the surface code. Incorporating a bosonic bat model, we also simulated surface code with a noise model and created a set of data with new error patterns. In the early fall semester, our group finished setting up all the models by developing the GNN and CNN models, trained them with the simulated surface code and the noise model, and evaluated the model's performance, which you saw on the previous slides. Thank you to Dr. McMahon and the ASDRP staff. That's all.
All right, so does anyone have any questions about this presentation?